To do, remember, is we have to recall what the polar plane is, and the polar plane is based on our middle guy, which is our pole. We also have what we call our initial side, where all the angles begin. And when we go to plot points, we use our unit circle to assist us. And so, can anybody help me out? How did you plot the point negative 3 pi over 3? Who wants to help? What did you do in words? Yeah, Anna, go ahead.
Find the angle of pi over 3, and then since which is like in the first quadrant.
Find the angle pi over 3, which is in the first quadrant, which is at 60 degrees, right?
And since it's negative,
So this is the positive direction, pi over 3. This is the negative direction, so you go down 3 units, which puts you on the third circle, because remember, our polar plane is based on distance from the pole, so you should be down here in quadrant 3. Everybody's good with that? Anybody need polar paper today? Anybody want some extra polar paper today? Polar paper? Polar paper? Okay, so then we have to do the second part, which is anybody else? You guys want some? Anybody else? Anyone? So our second part is to convert it into Cartesian coordinates. Cartesian coordinates. Anybody else? Why not? It's free, right? Anybody? Yeah? Yes, sir. We're going to do some graphing today, so it might be helpful. Here we go. I'm going to leave it up here. You guys are welcome to come up at any time and grab it. Okay. Who converted? Who converted for me and got numbers? Everybody did the warm-up, so everybody converted. Kyle, explain to me, what did you do to convert?
So to convert to Cartesian, you gotta make it into x and y. So your formula for that is r cosine of theta equals x, and then r sine of theta equals y. And then at that point you just plug in your r value, your theta value given, which then equals in the end of x equals negative 3 halves, and then y equals negative 3 times the square root of 3 over 2.
Beautiful. Beautiful. You used your conversion factors. X equals r cos theta, y equals r sine theta. You either have it memorized or you draw yourself a little right triangle and you just find x over r is cosine theta, y over r is sine theta. So you have your conversion factors right there, okay? I will not give you those conversion factors on your test, right? So you need to be able to make that little right triangle and do those conversions, okay? So that's something you need to know. All right, so you have your 2 conversion factors, and then you go ahead, and I am giving you your unit circle, though, okay? So on the back, you look at cosine pi over 3. Cosine is your x value. That's 1/2. So negative 3 comma pi over 3 converts into the x value, negative 3 halves. And the y value is negative 3 times the sine of pi over 3, which is square root 3 over 2. And as Kyle so nicely said, that's negative 3 square root 3 over 2. So converting into Cartesian coordinates, everybody should be getting the point. Negative 3 halves, negative 3 square root 3 over 2. Any questions at all on our? Give me an example. Somebody give me an example of a parametric curve. Yeah, Griffin.
X equals 3t squared plus 2.
X equals 3t squared plus 2.
And y equals 4t cubed plus 12.
Beautiful. Beautiful. A wonderful example of a parametric curve. How do we know we have a parametric curve? We have 2 functions, if you're in 2 space, 3 if you're in 3 space, where those functions are each functions of a third variable, which we call our parameter. So for the parametric curve that you gave us, what's our parameter? What letter's our parameter here, Griffin? It's t. So we have x defined as a function of t and y defined as a function of t. Okay, I'm going to ask one more question. All right, so if I have a parametric curve and I have x defined as a function of t and y defined as a function of t, can you do me one favor and somebody give me, different than Griffin, the first derivative? How would I get the first derivative? What would I do? Yeah. Oh, Kyle, you already go. Alex, turn. Alex, go. dy dx. Okay, good. So to get the first derivative, we would take dy dx, if we're reviewing a little bit. And what is dy dx? Yeah?
It's the derivative of y equals the, oh no, you're asking me the actual answer.
Mm-hmm. It's dy, go ahead. No, I want you to tell me what the formula is. It's the...
Oh, it's dy over dt over dx over dt.
Yep, dy dt over dx dt. Perfect. And somebody else want to help me out here. What's dy dt? Who hasn't said anything? This one's easy. This is a giveaway. Megan, go for it. 12t squared over 6t. And we could reduce that down to be 2t. Perfect. Perfect. So we know how to work with parametric curves. We understand that a parametric curve consists of an x value and y value, both of which are functions of a parameter t. And we understand how to get the first derivative, which is the slope of the tangent line to the curve. Okay? Because those are important pieces of information. What we're going to do today is take that knowledge and apply it to polar curves. Okay? We're going to take that knowledge and apply it to polar curves. Why do I do that? Because if you take a look at what Kyle told us a minute ago, do you see that every polar curve can actually be rewritten in terms of x and y coordinates, where x is a function of something and y is a function of something? In this case, our parameter is not t, but what's our parameter going to be? Yeah, Griff?
R.
Close, close, very close, very close, very close, very close. R is a radius, and what we're going to discover is R is actually a function of the same thing that this is a function of. And what we're going to discover very quickly is that x and y are both functions of theta, and theta becomes our parameter for each of these parametric equations. All right, so let's discover some things. Okay, one more thing. Last time we graphed, so again, a second warm-up, and if you have Desmos handy or your phone handy, you can use it. Okay, I will give you these graphs on the test, okay, but I haven't. I will give you these graphs on the test because I'm not expecting you to be able to graph them. But can you sketch the curve for me? R equals, what do I want to do? 2 cosine 3 theta. Can you guys sketch that curve on the polar plane for me? So again, you can use Desmos or a graphing utility to help you. If you have a graphing calculator and you know how to graph in polar on your graphing calculator, you're welcome to pull that out. Your phone works just as nice. You can either download a Desmos app or you can just pull up Desmos. What does R equal 2 cosine 3 theta look like? This is something we looked at very briefly at the end. This is how we define our polar curves. Remember, our polar curves are based on 2 letters, or our polar points are all based on R and theta. And so we would actually say, and Griffin, this, I just want to show you because I know you're really bright and you see what's going on here. R is a function of theta. So in a way, R is based on this theta as well, just like the cosine of theta. What are you guys getting as your picture when you graph this? Let's pull up Desmos. Okay, so I've got my left PC, and that's going to this place here. Yeah, okay, good. And in Desmos, remember, you can go up, just to remind everybody, up here in the wrench, it allows you to change and convert from XY or rectangular coordinate systems into polar systems. So you can just click right over there. Awesome. And now we're going to put in the function R equals cosine of 3 theta. And you guys got what's called our rose curve? So the picture that we get is a rose curve. And let me just put it up here to be in our notes, but you guys can see this up here on the sketch. So now I'm going to ask you a question real fast. Okay. And this is where we are going to be doing lots of critical thinking and analyzing, Kyle.
You forgot the 2 when you put it in R2.
I did forget the 2. Thanks, Kyle. Thank you. Thank you. I did forget the 2. What does that do to it? Yeah, what does it do?
Doesn't it make it bigger so it's touching the 2?
Yep. It stretches it out so that each of those petals go not to 1, but they stretch out to 2 units. Thank you. All right, so here's our rose curve. And we are going to play with these curves today and apply some calculus, which is why I kind of reviewed a little bit about parametric equations and things like that, but I think I went ahead a little bit too fast. So here's my first question, because we're going to do what? We're going to, of course, take a curve like this and find the tangent lines, right? The tangent lines to this curve. Then we're going to find the area inside these petals and get the area inside this curve. So we're going to do maybe even arc length. We'll see how fast we go. Okay, good. So, first question. Are you ready? Let's pretend we're a point. So, if these are parametric curves, because they're like parametric curves, let's say we're a point and we're traveling along this curve all the way around it. Are you with me? So we start, we go all the way around it. How many times, we're going to go and make the whole curve. How many times does that point pass through the pole? Are you with me? So put a point on this curve. Let that point go around the curve. Are you with me? Tracing out that curve. Does that make sense to everybody? I want to know how many times does that curve intersect the pole? Critical thinking caps on. We haven't talked about it, haven't given you a process. I'm just looking for thoughts. There is no bad thought here. What do you think, Kyle?
Should it just be 3?
Why?
Well, it's like, okay, if I trace over it,
Okay.
kind of like my finger or pencil.
Okay. Okay, here we go. I'll put my finger on here. I'm a pencil. Where do you want me to start?
Just start at 0, 0.
Okay, start at the pole.
The pole, and then just start to your right.
Right here? Start right here instead?
Start at the pole, move to your right.
Start at the pole and move to my right. This way or this way?
Up. It doesn't really matter.
Oh, which way is the curve going? Do you know by any chance? Oh, well, anyways, doesn't matter. Okay, so let's just do it. Here we go. Ready? I was just asking a question. Okay. So now we go. So this counts as 1. We start at the pole. It hits 1 time, right?
If we start at the pole, it's 1.
Oh, okay. We will pretend like we're starting just off of it. How's that sound? Okay. So here we go. Ready? I'm tracing.
That's 1.
1.
That's 2.
That's 2.
And 3.
Huh. And when I get back here, I have to hit 3
Then
times.
start at the pole.
Oh, that makes sense. What do you think? Would you guys all say 3? Okay. I say 3. On the interval, then let's be specific here. So on the interval, not including 0, okay, but including pi, we say that the curve hits the pole 3 times. I like your reasoning. Did anybody do it differently and come up with 3? That makes sense. Anybody do it differently? Anybody use trig? Of course not, right? Are you kidding me? Use trigonometry. Oh my God. Okay, so first of all, everybody tell me, when the curve's at the pole, what is the R value? right? When my curve is at the pole, the radius, the R value has to be 0, right? Whoever said 0. Beautiful. Who said 0? Who is that 0? Anand. All right. So 0 equals 2 cosine theta solves the problem of finding out when we're at the pole. We want to know when 0 equals 2 cosine theta. Haha, trigonometry, right? Okay. How do we solve this trigonometric equation? What would we do to each side? We would divide each side by 2. I think we need to review this, okay, because you're going to have homework on this, so let's review this. So 0 is cosine of 3 theta. How do we solve that trigonometric equation? Critical thinking, caps, right? Well, we do this. Are you with me? You are going to ask yourself, what angle would you have to put in here so that the cosine of, this is the way I look at it, okay? You don't have to look at it this way, but this is the way I look at it. I say, okay, what would this have to be so the cosine of that gives me 0? That's the way I think about it. So what angles, so that when you take the cosine of that angle, you get 0? Where places? Give me some places. Griffin, go ahead. Pi over 2. So the angle would have to be pi over 2. Can you give me another place? I need to get at least 3, right? Because we know, just by knowing intuitively, we have to go 3 places, right? Kyle, where's another one? 3 pi over 2. Chris, you go to give me my third one. Oh, no. Okay, no, he did. Huh? No, not Kyle. Somebody else give me different. Somebody who hasn't said anything today. Who knows trig and loves trig. Who likes my trig? Where's the next place? Pi over 2 is one place. 3 pi over 2 is one place. Negative pi over 2? Yes, it would be. I would count negative pi over 2, except I want to stay positive quick. Hang on, get me biggers. Mooney, I got one. 5 pi over 2. Yes, negative pi over 2 would work, except I threw a little trick in here and made you all positive. But you are on the right track. 5 pi over 2. 5 pi over 2. Absolutely 5 pi over 2. But you got the idea. You exactly know what to do, guys, right? Anna.
From 0 to 2.
Well, let's see.
Because 5 pi over 2 is...
It is too big, isn't it? Good question. This is both of these are outside 0 to pi. But hang on, because I did this all wrong. I don't want t between 0 and pi. What should t be, guys? I already goofed it up. What should t be? T should be what? Our parameter, which is theta. So first of all, big goof, Tina. That's supposed to be theta, okay? Secondly, this is not quite theta yet. This is just a big question mark. What is this question mark holding the place for? 3 theta. Do you guys see that? So really, what I'm asking is, where is 3 theta equal to pi over 2? Where is 3 theta equal to 3 pi over 2? And where is 3 theta equal to 5 pi over 2? If we were going negative, Chris, 1,000%, I would have to include negative pi over 2. I would have to include negative 3 pi over 2. Do you see what I'm saying, guys? So multiple angles here. So now, and you're right, Anna, I love that you said, be careful, Tina. We have to make sure our final answers lie within 0 to pi, right? And sure enough, guys, are you guys dividing for me? What are you getting? Pi over 6? What are you getting on the next one? Griffin. Pi over 2. And the next one. And 5 pi over 6. And do they all lie within 0 to pi? Is that not nice? And I've got how many? 3 of them? So, how many times does this curve hit the pole? It hits 3 times. Where does it hit? It hits at the angles 0 equals pi over 6, if I was to graph this, okay? If I was to graph this curve, 0 to pi over 6, pi over 2, and 5 pi over 6. And if I want to show and convince you of that, I could go to Desmos and I could put 0 and I could put pi divided by 6. And you would notice that what happens is that if you start at 0 for your value on your parameter, you're actually starting over here on your polar curve, and you're going and you're hitting here. Do you see what I'm saying? Everybody see that? Put this in your notes somewhere because we're going to need it, okay? 0 to pi over 6 starts us over here, brings us back, and hits us at the pole, okay? And, Chris, I'm going to go off your idea, though. Let's say I was going outside that range. What value would give me this guy here to get the bottom would be negative pi over 6, like you said. So if I'm starting here from 0 and going to pi over 6, going in the negative direction, the next angle that I would have would be negative pi over 6. And that actually gives me one loop on the curve. My next loop would go from pi over 6 to pi over 2. So if I change, are you all with me? Are you understanding? Are you seeing what I'm doing here on Desmos? If I take my next limits that I did mathematically and went from pi over 6 to pi over 2, it gives me the next leaf. Are you with me? Etc., etc., etc. Are you ready? So we'll move forward, we'll come back, and we'll hit that again. But we're going to do some calculus with polar curves quick. Specifically, the first thing I want to do is I want to talk about tangent lines. When you talk about tangent lines, we always are talking about xy, dy, dx. We write our lines in Calculus 2 with y's and x's. When you get to Calculus 3, you're going to have a whole new coordinate system, meaning you're going to do everything based on vector value functions. So you'll learn something different there. But right now, in Calc 2, we are going to take, and everything has to get converted into xy in order to find tangent lines, because we know that the equation of a line is what? Y minus y1 equals m times x minus x1, right? So that's what we're going to be using. And we also know that, for our purposes, the first derivative is equal to the slope of that tangent line. Okay, so we know all that. So let's put it together with what we're learning. As Kyle told us, we learned 2 conversions last week. X equals r cosine theta, y equals r sine theta. And in our polar curves, what do we know about r? R is said to be a function of theta. R itself is a function of theta. R is defined by functions of theta in polar curves. Do you guys see that right there? So another way we could rewrite this is we could say that x is a function of theta, and we have r of theta cosine of theta. So x of theta is r of theta cosine of theta. All it's saying is the same thing, except we're actually physically putting in that whole concept of x is itself a function of theta, r is itself a function of theta. So let's spell that out right there. X is a function of theta, x depends on theta. R is a function of theta, r depends on theta. Cosine is a function of theta. And so for that first equation, we see that we have a parameter of theta. Which is going to be the same parameter when I go right here, right? This is what's creating this parametric curve. Y of theta is also r of theta times sine theta. And so I can view x of theta and y of theta together as a parametric curve with a parameter of theta. Are we okay so far? Now, why is this important? This is important because we are trying to get dy dx. And so we know how to get dy dx when we're dealing with parametric curves. So by changing this into a parametric curve, we can easily decide what dy dx is for our polar curve. On your test next week, you will be required to show me this proof right here, okay? I'm going to give you the formula. If you look on your notes, I gave you last week a formula sheet, and I just lost it. Where did my formula sheets go? So who was not here on Wednesday? Oh well, don't tell me because I don't have my formula sheets anyways. I lost them! Where'd they go? Hang on, let me see what I got here. On Wednesday, I handed out a big, long, nice, fancy formula sheet. Well, I'm glad I handed them out to you because I don't have one. I will have to print some more out for people that did. Oh, here they is. 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 And so, if you look on that, who needs one? Who was not here on Wednesday and needs one of these big long sheets with the unit circle on the back? Everybody's okay? So, can you guys go down here, and we are going to talk right now about finding the equation of a tangent line. And to find the equation of a tangent line, we need the slope of a polar curve. Do you see that? Yeah, Joel, need one of these? So, everybody sees, if they go down to the 1, 2, 3, 4 box, do you see the slope of a polar curve in there? Do you see the slope of a polar curve? Do you see that messy equation? One of your test questions will be for you to start with rewriting x and y as functions of theta, and then deriving this formula, which we're going to do right now, okay? It's not hard, okay? But it takes you thinking a little bit. Are you with me? Okay. So I'm going to go through that whole entire problem that you're going to figure out what to do for your test. All right. Here you go. Are you ready? If I want to find the tangent line to a polar curve, I need, just like before, to use y minus y1 equals m times x minus x1. So one of the key pieces is I need my first derivative. My first derivative is dy dx. And in parametric form, like Alex just told us, normally it's dy dt divided by dx dt. But that's when t is my parameter. So what's my new parameter? Somebody who hasn't said anything. What's my new parameter? Yeah, thanks. Yep, Taylor, theta. My new parameter is theta. So what is dy dx in terms of theta? It's going to be what? Not dy dt, but absolutely. So it's dy d theta over dx d theta, right? Okay, good. That's just from parametric curves, right? Okay, alrighty. Somebody who hasn't said anything, dy d theta. What is dy d theta? It's the derivative of y with respect to theta. But this derivative involves r of theta and sine of theta, both of which are functions of theta, which means I have a what going on? I have a product. Are y'all with me? So somebody tell me, what is the derivative of y with respect to theta applied to a product? Hint, uses the product rule. Somebody who hasn't talked, I want you to tell me, what am I going to do to get dy d theta? I need my product rule, right? This is my first function. This is my second function. And remember, how do you get the derivative of a product? You take derivative of the first times the second plus derivative of the second times the first, right? Okay. So somebody walk me through dy d theta. Anybody want to try? Who hasn't talked yet? Yeah, William, go for it. Yes, it would be. So derivative of the first, dr d theta, times the second, plus, keep going. R of theta, which is f, right? Times the derivative of sine, which is cosine. Beautiful. Beautiful. Who wants to do the bottom for me that hasn't talked yet? Who wants to, Lily, you want to? Okay. Product rule for dx d theta. Dr, hang on, whoa, you're going faster than me. Dr d theta, which is the derivative of the first times the second. Where'd you get the minus sign? Because the derivative of cosine is minus sine. So then you take f times g prime, derivative of cosine is minus sine, and there we go. And so when you're looking for the slope of a tangent line, when you're given a polar curve, this is the formula right here. Do you guys see it? Interesting. So on your test, what am I going to require? I'm going to require you to either show me the product rule, okay? To show me the product rule. Write this step along with applying the product rule, you get this. Are you with me? But I will require you to go through and get me all of the steps here. Now, you're going to have this on with you on the test. I'm almost thinking I don't want to give it to you. I'm almost thinking I should erase that, I think I might erase that and have you guys derive it. That is exactly what I think I might do. We'll see. That's exactly what. How is that hard? That's not hard at all. We'll see. I'm very tempted to erase this and have you fill this in. Ooh, I am so tempted to do that. I might do that. Okay. I think that might be what I do. Make sure you understand how to get that. Any questions? Yeah, Kyle.
Would we ever have to find the second derivative for this?
Here we go. Find the slope of the tangent line to the polar curve r equals sine 4 theta at theta equals pi over 8. Find the slope of the tangent line to the polar curve r equals sine 4 theta at theta equals pi over 8. Okay. Step 1, we're just looking for slope, not asking you for the tangent line. So all you have to do is plug that formula in or write that formula down, which is your slope formula, right? And I like to derive it each time. That way I have practice deriving it. So you don't have to do this, but I'm actually just going to write down it. So x of theta is r times cosine. Y is r times sine. And I know that to get dy dx, I need to take dy d theta over dx d theta, and I will apply the product rule. Dy d theta is the derivative of r with respect to theta times sine of theta, plus the derivative of sine, which is cosine, times r. Dx is the derivative of r with respect to a theta times cosine theta, plus r times the derivative of cosine, which is minus sine. So my very first step is to make sure I know what the dy dx is in terms of r's and thetas. Yeah, I've already decided in my head. I'm going to erase this. You guys will have this big blank, and part of your job will be to fill that formula in, okay? I think that's a little bit of calculus that I can expect. Yes. Huh. Now what do we do, guys? Now what do we do? What do you want to do? Find your stuff, right? What's DRD theta? What's DRD theta? I don't have it back here because I see we did DRD theta. Very nice. DRD theta is 4 cosine 4 theta. Yes, it is. DRD theta is 4 cosine 4 theta. DRD theta. That's really all you need. That's really all you need, because that tells me then that DRD theta is 4 cosine 4 theta. Sine of theta is just sine of theta. R is just sine of 4 theta. So all I'm doing now is I'm replacing. DRD theta gets replaced with what it is, 4 cosine 4 theta. R gets replaced with what it is, sine of 4 theta. And so that gives me the following. 4 cosine 4 theta sine theta plus sine 4 theta cosine theta all over 4 cosine 4 theta times the cosine of theta minus sine of 4 theta times sine theta. Now, I am not going to make you go any farther if it comes to simplifying. This would be the slope of the tangent line. So we would say that is the slope of the tangent line for the point r theta. It's 4 cosine 4 theta times the sine of theta plus the sine of 4 theta cosine theta. 4 cosine 4 theta cosine theta minus sine 4 theta sine theta. So all we did was put substitution in. And then, of course, the last thing, and you guys might already have a number for me, the last thing you want to do is evaluate this at pi equals 8. So theta is pi equal 8. You guys got an answer for me? Of course you do. 4, cosine. Notice you want to be very careful. If there's a 4 in there on the theta, you have to make sure you multiply before you evaluate. Cosine of pi over 2 is 0. The cosine of pi over 2 is just 0, which means this whole term drops out, right? Because it's all 0. Same thing happens down here. 4 pi over 8 reduces to pi over 2. That's 0, so this whole term drops out. And that just leaves us with the sine of pi over 2. What's the sine of pi over 2? 1. Thanks, Brandon. Yep. And the sine of pi over 2 is also on the bottom. And so that just leaves me on top with the cosine of pi over 8 divided by negative sine of pi over 8. And if you so feel like using a little bit of your trigonometry, convert that cosine over sine into cotangent. Pi over 8 is not on our unit circle, okay? I will not expect you to put a value in because it's not on our unit circle, all right? And also, when you go into web work, it will accept an answer just like this. You don't have to go down. Don't approximate it. Don't waste your time pulling out a calculator. Just stick this correct directly into your web work, okay? So that would be the slope at sine of 4 pi at t equals pi over 8. Questions? Not very exciting, but I wanted to at least go through one together with you before I give you one to try. Who has a question? Any questions? Okay, no questions, right? So I'm going to give you a practice problem. Another practice problem, all on your own some. I want to take this curve right here, r equals 2 cosine 3 theta. And we're going to look at one time around. So that goes from an interval from 0 to pi. And I want to find, notice it hits it 3 times, right? It hits it 3 places. So we have a tangent line to the pole that goes here. We have a tangent line to the pole that goes here. And we have a tangent line to the pole that goes here. Do you guys see what I'm saying as far as tangent lines go? So we got a tangent line here, a tangent line here, and a tangent line here. Now this one is, what do you call it? It's not fun, it's not important, it's not exciting, because it's just a vertical tangent line. I can see I have a vertical tangent line right there. But I would like to know, what is the tangent line to the curve right here? And notice we discovered that that's when pi, or the angle, is pi over 6. So your problem is this. Write the equation, that would be too easy, wouldn't it be, huh? Oh well, we're doing it anyways. Write the equation of the tangent line to the curve when theta is pi over 6. Write the equation. Okay? Alrighty. I'm going to wander. You let me know if you have any questions at all about the steps on what you need to do. Thank you guys for doing your surveys. Thank you, everybody. It's funny. Everybody learns a little different. Some people love group quizzes. Some people hate them. Some people like recitation a whole lot. Some people find it, okay, it's helpful, but not super helpful. So it was really nice reading about everything that input people gave. One of the most common things was you wanted more problems to work on your own in class. And so I do want to try and make that happen, whether it be problems in this class or recitation, but people also wanted web work problems that might be more challenging to work those in class as well. So I will try to honor those as best I can. So here we go. We've got a curve. We are finding the equation of the tangent line to the curve. So first thing is you're getting your slope. So you are writing down your slope formula. dy dx is dr d theta times something. That, if it's on the unit circle, I want you to give me. Give me a tangent line. And you know you did it right if when you graph that tangent line with y and x, on the same graph as that polar curve, it's going to look like it's a tangent line. Very nice. So now you got yourself right. So now how do you get your equation? Y minus y1 equals m times x minus x1. So now you need your point. Matches, huh? Nice. Who's got questions? I think you guys have this down. From what I can see, everybody's getting the slope. Everybody's getting the equation of the tangent line. Yes. You could, or since I already did a little bit of work, we could use our noggin. We know that pi over 6 is where you hit the pole. So you actually already know the point, but yes, if you didn't, then you would take t equal pi over 6, and you would plug it back into x and y, to your x and y. Yep, and that would give you your x value, and that would give you your y value. Absolutely. Absolutely. Very nice. All right, see if you guys are matching me. See if you guys are matching me. Okay, so x equals r cos theta, y equals r sine theta, dy dx. You guys have as a formula derivative of the first, which is going to be dr d theta times the cosine of theta plus r of theta times sine of theta. Nope, undo, Tina. You did it all wrong already. That's sine of theta. That's derivative of sine, which is cosine. This is dr d theta. That's times cosine, and then the derivative of cosine is sine. So what you guys are, and then you're getting over here, you did dr d theta, and you came up with 6 sine 3 theta with a negative in front. So dy dx, you guys got to be dr d theta, which is negative 6 sine 3 theta times sine of theta plus 2 cosine 3 theta cosine of theta all over negative 6 sine 3 theta cosine theta minus 2 cosine 3 theta sine of theta, and then you guys all plugged in theta equals pi over 6, and I did it wrong again in my notes. It should be theta, not t. Goof. So that is negative 6 sine of 3 pi over 6 times the sine of pi over 6. Good problem, because it's going to help you if this angle is on your unit circle. Because I'm giving you a unit circle, I want the exact value. No approximations, no calculator values. I want you to tell me what's the cosine of pi over 6. You see what I'm saying? I want you to actually give me some good numbers to work with, since I'm giving you the unit circle. Okay, so 3 pi over 6 just reduces down to pi over 2. 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 So that's giving me negative 6 times the sine of pi over 2, which is 1, times the sine of pi over 6, which is 1/2, plus 2. Cosine of pi over 2 is 0. Cosine pi over 6 is square root 3 over 2. On the bottom, negative 6 times 1 times square root 3 over 2 minus 2 times 0, 1/2. And that's just giving us negative 6 times 1/2 over negative 6 times square root 3 over 2, which just goes down to 1 over square root 3. Is that what you guys got as your slope? I think I saw that. 1 over square root 3 as your slope. Now, we did already talk about this earlier today. When theta is pi over 6, we are at the pole. And if we're at the pole, x is 0 and y is 0. But let's say we didn't know that, and I'm now going to write the equation of my line, y minus y sub 1 equals m times x minus x sub 1. How can I find that value if I don't already know? Well, I can take my x and put it back into my original equations and plug everything in and find it that way. But I'm not going to take the time. I'm simply going to say I know it's 0 because I know I'm at the pole, and therefore y is 1 over square root 3x is my tangent line, and let's make sure that works. Did anybody do it on Desmos? Does it look nice and neat? Ha! Hello, beautiful tangent line. That is one of the tangent lines to the curve. The other one, what do you think the other one's going to be? We can just guess now. It's going to be what? The other tangent line at the pole. Y equals negative 1 divided by square root of 3. Yep, it is. Yep, it is. And what's the third one? What's the third tangent line right there at the pole? If I'm looking for velocity, or if I'm looking for the first derivative, it's going to be the horizontal. Excuse me, that's not horizontal. The vertical line. What is that one? Yeah.
X equals 0.
X equals 0. X equals 0. X equals 0. So if I wanted to find all three equations, there are my equations for my tangent lines. X equals 0. Y equals 1 over square root 3x. Y equals negative 1 over square root 3 times x. Ha! Ha 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 ha. Ooh, we have 20 minutes. 20 minutes. Who's got questions? How are yous? You will need to find slopes for your homework. You will need to find, I think I have to do at least one equation of a tangent line. I'm not sure, but I'm pretty sure we do. Okay. Questions? How are we? Feeling good? Okay. So that's the first piece of calculus. Always finding first derivatives, finding slopes of tangent lines. The other piece of calculus that we do is find areas, right? The areas within a curve, which involves not derivatives, but integration. Integration. Okay, so we're applying integration now. Okay. Yay! Are you happy? Okay, so let's talk. Well, hang on. I went really fast. Any questions? Let's talk before we actually come up with a formula, because I gave you a formula sheet, right? I will give you those formulas. I will not ask you to derive those formulas for area. That's all the way down the bottom of your sheet. But again, I will have you derive this slope formula for me. You're going to have a blank box when I give you this formula sheet, and you'll have to actually derive that, okay? Okay. All right. Okay, so here we go. Ready? Area. Do you see the formula that's on there? Can somebody read for me the area within a polar curve? So basically, if you have these polar curves, you notice that they look kind of funky. Sometimes they're circles, sometimes they're heart-shaped things, which we call cardioids, okay? Sometimes they're rose curves, and you'll be asked to find the area within one rose curve, okay? But in generally speaking, you're going to be asked to find an area within a curve instead of under a curve. Like we do with XY plane, we look for area under a curve. In polar plane, we look for area within a curve, okay? And so if you look on your formula sheet, there is a formula. And it says something like this: alpha to beta, 1/2 r squared d theta. So you have a formula, but I always, and Quinn's not here, he likes to understand where everything comes from. So let me just give you a little background of where this comes from, okay? In the XY plane, if we were to find an area, what did we do to create area under a curve? Do you guys remember from Calculus 1, what did you do? You created a sum of something. What did you add up? You broke this area up into what? When we talked about where the formula came from. Munia. Rectangles. You took and made a single rectangle, and then another rectangle, and then another rectangle. Do you guys remember doing this? Okay? And then you created what was called the Riemann sum, which was the sum of the area for each rectangle. And it worked out to be that any specific rectangle, are you with me, had a height and a width. And you called the width dx or delta x, and you called the height, well, in this case, it's just the function value. F of x is the height, dx is the width, and when you take a width times the height, you get an area of a rectangle. This is what you did. And then you added them all up, right? And so we use the sigma notation, which we're going to use in 2 weeks, 3 weeks, 3 weeks. We'll have this sigma notation, and what that does is it adds them all up. Now I'm being sloppy here, but I'm giving you the general thing. And you add them all up, all the rectangles up, and that gives you an approximation of the area under the curve, right? That gives you approximately, when you add up all these rectangles, the area under the curve. And then what did you do to make it exact? We made what happen? Our delta x go to 0, right? And so we took a limit. Hello there, beautiful limit. We know what a limit is. And we took a limit. And you guys probably don't remember this at all. And this is where your entire integral comes from. This is where integration comes from. It comes from taking a limit of areas of rectangles under the curve all added up. And that's where this whole integration thing comes from. Now, we are not in XY space. We are in polar space. And so if I'm going to take a curve in polar space, it's kind of circular, and I take this curve, and let's say I want to find the area inside this curve, and maybe it goes like this or however it goes, okay, and I want this area. Instead of breaking it up into rectangles, what I'm going to do is break it up into segments of a circle. So instead of rectangles, what I'm going to do is I'm going to break this up into segments of a circle. And we're just going to make this, all these segments, are you with me? We're going to add up all these segments that I'm breaking it up into. Same idea as rectangles. And then what I'm going to do is find the area for a segment, which is different than the area of a rectangle. And then I'm going to take this here as my delta theta, and I'm going to shrink that to 0, and that's what's going to give me the area in the curve. Now, I have some really nice notes for anybody